Across the vastness of space, rare cataclysms unleash bursts of energy so intense they dwarf entire galaxies. These events are known as gamma-ray bursts, or GRBs, the brightest explosions observed in the cosmos. For a few seconds to minutes, they outshine everything else in the gamma-ray sky. Occurring billions of light-years away, they signal the violent deaths of massive stars collapsing into black holes, or the collision of neutron stars, dense stellar remnants with unimaginable gravity. But what if one of these cosmic titans were to point its lethal beam directly at Earth? What happens if a gamma-ray burst hits our planet? This is not just science fiction. Astronomers have found evidence that GRBs have happened before in our galaxy, and some may have influenced Earth's biosphere. Today, we embark on a journey to understand these terrifying cosmic phenomena and their possible impact on life here on Earth. Gamma-ray bursts are born from some of the universe's most extreme events. As these jets pierce through the collapsing star or debris, they release colossal amounts of gamma radiation, a form of electromagnetic radiation with energies millions to billions of times higher than visible light. To understand the scale, consider this. The energy output of a GRB in a few seconds can equal the sun's entire lifetime of radiation over 10 billion years. Yet, this energy is focused in narrow beams, like cosmic laser pointers. Most GRBs occur far away, safely outside our solar system. But what if one were aimed at Earth? The Milky Way is home to hundreds of billions of stars, some of which will end their lives as GRBs. Luckily, the narrow beams are highly directional and rare. Statistically, a lethal GRB aimed directly at Earth might occur once every several hundred million years. Earth's atmosphere and magnetic field provide some shielding, but gamma rays at these energies can penetrate and cause chemical changes in the upper atmosphere. Scientists studying ancient mass extinctions have speculated that past GRB events may have contributed to massive die-offs, such as the Ordovician extinction 450 million years ago. In 2004, a giant flare from a magnetar, a type of neutron star, occurred in a nearby galaxy, briefly affecting Earth's atmosphere despite the 50,000 light-year distance. These cosmic warnings remind us that GRBs are not just distant curiosities, they are potential natural hazards. Imagine a GRB jet aimed directly at Earth. Within seconds, an intense beam of gamma radiation sweeps over the planet, passing through the upper atmosphere. The immediate effects begin in the stratosphere. Gamma rays interact with nitrogen and oxygen molecules, breaking chemical bonds. This leads to the creation of nitrogen oxides, NOx, powerful compounds that catalyze the destruction of ozone. The ozone layer, Earth's shield against ultraviolet radiation, rapidly thins. Simultaneously, the ionosphere, the electrically charged layer in the upper atmosphere, is heavily ionized, disrupting radio and satellite communications. Satellites may suffer damage or fail entirely due to high-energy particle bombardment. At ground level, the gamma rays themselves are mostly absorbed by the atmosphere, so direct radiation exposure to humans is minimal. However, the disruption to atmospheric chemistry sets the stage for a cascade of secondary effects. The ozone layer's rapid depletion opens a deadly window to ultraviolet B, UVB, radiation from the sun. UVB is known to damage DNA, cause skin cancer, and harm plant life. Without ozone's protection, the Earth's surface is bombarded with UV radiation levels far beyond normal. Marine ecosystems, particularly plankton and phytoplankton, suffer immediate damage. These microscopic organisms form the base of the oceanic food chain and play a critical role in carbon dioxide absorption. The die-off of plankton disrupts marine ecosystems and reduces oxygen production. On land, plants experience increased mutation rates and reduced photosynthesis, impacting agriculture and natural vegetation. Animals dependent on these plants and marine life face starvation and habitat loss. The elevated UV radiation also impairs insect populations, crucial for pollination. The chemical reactions triggered by the burst don't stop with ozone depletion. The increased nitrogen oxides lead to the formation of nitric acid aerosols. These aerosols reflect sunlight, causing a temporary global cooling effect, similar to volcanic winters. At the same time, nitric acid precipitates as acid rain, damaging soils, freshwater ecosystems, and vegetation. The acidification of rain impacts lakes and rivers, threatening fish and amphibians. The combined cooling and acid rain effects stress ecosystems already weakened by increased UV radiation. Radiation and environmental stressors cascade through living organisms. DNA damage leads to increased mutation rates, cancer incidence, and reproductive failures. In the oceans, coral reefs bleach and die, fish populations decline, and entire food webs collapse. Terrestrial animals suffer from skin and eye damage. Amphibians, already vulnerable, see population crashes. Insects critical to pollination decline, further impacting plant reproduction. Agricultural crops face stunted growth and yield loss, threatening food security for humans. The combined biological impacts could lead to widespread extinctions and ecological upheaval. Human health is indirectly affected by food shortages, increased disease, and environmental disruption. Fortunately, Earth's systems are resilient. The ozone layer begins to recover over decades as nitrogen oxides are removed by rain and chemical processes. UV radiation levels slowly return to normal. Ecosystems adapt or repopulate, some species going extinct, others evolving. Global temperatures rise back as aerosols dissipate. Human civilization, if prepared, can mitigate many impacts with technology, such as artificial UV shielding, protected agriculture, and healthcare. But recovery is slow. The scars of a GRB event would be etched across the biosphere for centuries. Such an event reminds us of the delicate balance sustaining life on Earth. Modern astronomy monitors the sky continuously for GRBs. Space telescopes like NASA's Swift and Fermi observatories detect bursts within seconds, alerting the scientific community. However, because GRBs last only seconds to minutes, there is minimal warning if one's beam points at Earth. Future technologies might allow early detection of progenitor stars entering final collapse phases. International cooperation is key, as a GRB impact would affect all nations equally. While devastating locally, gamma-ray bursts play a role in shaping galaxies. Their intense radiation can sterilize regions of star-forming clouds, influencing where and how stars and planets form. They may contribute to regulating life's emergence by culling biologically hazardous zones. In some ways, GRBs are agents of cosmic evolution, harsh but necessary. Understanding them offers insight into the rarity and resilience of life in the universe. We are lucky that Earth's cosmic neighborhood has been mostly spared. Scientists ponder the question, could humans survive a direct hit from a nearby GRB? Technologically advanced civilizations might shield themselves in underground bunkers or magnetic fields. Artificial biospheres could protect critical life support systems. Space colonies orbiting other planets might be unaffected. Some imagine using directed energy weapons or stellar engineering to deflect the progenitor star's collapse. While speculative, such ideas spur innovation and preparedness. The universe's threats inspire humanity's resilience. Gamma-ray bursts are cosmic fireworks, brief, brilliant, and terrifying. They remind us that Earth is not isolated but part of a dynamic, sometimes hostile universe.